Welcome back to this sub-lecture in the sequence of lectures on pedagogy. So the topic 3 according to our lesson plan is program design. So this topic and discussion of this topic at such an early stage is because of the observation in the literature, in the education literature, that many students report that they can understand the programming language, but somehow have a mental block when it comes to even starting to write a program. They don't know how to start. Okay. Students find the interaction between different language statements, say the for statement and the if statement, difficult to manage. So if they know many statements, they just get more confused. Okay, so should I use the for? Should I use the if? Should the if go outside? Should the for go outside? Whatever it is. So knowing too much is also a cause for confusion. Now, when we teach turtle programs, the primitives are very few. So you have the turtle movement, turning, and maybe not even pen up, pen down, okay, and repeat. So there really are two things that you have to worry about. And it is clear that the repeat is going to be outside of the turtle movement. I cannot say turn and inside the turn have put a repeat. Okay. So it is very clear that the turning will go inside the repeat rather than the other way around. So the number of choices, the number of design choices in writing the program is very small, and therefore perhaps at an early stage students might find it easier to write programs. So that is the motivation. Okay. So while many students complain, or it is their major problem that they don't know how to start, they are just overwhelmed by the language, the way we should look at it is, okay, they are overwhelmed by the language, then let us get them to write programs early on when they know only a very small number of statements. So assignment statements are enough, but repeat makes it a little bit more interesting. And so even with repeat, or even without assignment statements actually, just the turtle primitives, we find that students are completely at home. So the turtle drawing programs, programs for drawing pictures using the turtle, are the easiest programs for children to write. That has been my experience. Okay, so as far as program design is concerned, it is useful to show some full programs to students and ask them to modify those as well. But again, everything goes nicely if in the beginning we only use a small number of constructs. So the moment we talk about the first non-trivial program, we should do the discussion about program design. Okay. So our choice regarding this is calculation of E by summing the series. So this can be written using just repeats and assignments, and therefore it is a natural point at which to do this discussion. Okay. So it is done in chapter 4, and it's the third topic of the course. So to calculate E, the language complexity will not be a problem. The students will not get confused about, oh, what should I use? I have so many things, and which one is the right one to use? No, they only have the repeat and the assignment statement. But nevertheless, this should be taught in a leisurely manner. So we discussed earlier how to teach summing of the series for E. We discussed it at length. So remember what we discussed. We said first figure out what you would do by hand, figure out the structure. Okay, so is there a loop? What do you think happens inside the loop? Do all that exercise. Okay, so do that exercise in a leisurely manner and then write the program. Okay, so students actually appreciate the slow development. This is something that I have asked students who have read my book as well as students in my classroom. do you want me to go over this slowly, or should I just omit it, or should I just go very fast? So bright students as well as not so bright students have told me, please go over it slowly. This discussion helps us because it tells us what a full program is. A full program is sort of a different beast as compared to 10 individual statements as well. A 3-line full program is different from understanding 3 statements in isolation. So please go over this very slowly, and that would be my suggestion to you as well. So what is our recipe for program design, which we discussed last week? Understand the problem, create input-output examples, understand how you would solve the problem manually. Okay, state what values you calculate in each iteration. So in the ith iteration of ith term, Ti of the series is calculated. Okay, so all this you have to do. We have discussed it last week, and accordingly write the program. Okay, so discuss it slowly in the classroom. Okay, encourage students to write down the plan. What happens in ith iteration? Ti equals 1 over I factorial is calculated, or Ti equal whatever value you have associated with Ti gets calculated. What happens in each variable? State them. Tell them that stating plans is important for debugging. Should your program not work correctly, you should be able to figure out where things went wrong, and for that writing down the plan is really important. Okay, so the way the recipe goes, identify the variables you will need. Okay, and one point that can already be emphasized at even at this stage is the distinction between what to compute and how to compute it. What to compute is given by the plan. The plan says, well, I should clarify that. The plan will say something like Ti will be calculated. So the plan will talk about what values are going to be calculated. Okay? In which iteration, that is true, but they will name what values are going to be calculated. So that is the what. By what I mean what values. How is the code. So the student should be aware about both of these things. They should give names to the values. That is what it means to be aware. So what value is calculated in the ith iteration is distinct from where that value is stored. I might have the name T for the variable and Ti for the value, and the T's are same, but again the subscript says that this is a value. So there is a distinction between values and variables, and we should be clear about, are we talking about the value or are we talking about the variable? Now in this case homeworks are fairly natural. There are other infinite sums and products, very nice sums and products. And by the way, several of these sums and products have an Indian origin. There were Indian mathematicians from about 2000 years old as well, who have invented, or certainly 1000 years old, who have invented very nice formulae for lots of things that we think today are very modern. So do tell your students that there is an Indian connection. Okay, so I think programming discussion, design issues should get started early on, and you should continue to discuss them throughout the course. Continue to emphasize throughout the course that manual algorithms should be designed first before writing programs. Before writing programs, be very clear how do you solve the problem manually. Write down plans or invariants, at least for all the important loops. And yeah, so plans should be like invariants, and they should contain all the information that will help us in deciding whether the program is correct or not. Okay, so this takes some thinking, but at least you can ask the students, look, is this variable changing? Then why isn't that change reflected in the plan that you have put in? We cannot demand a formal proof of correctness because that is quite laborious. Okay, but at least the thought that went into the design. The thought must have been something like that: in this iteration I will calculate this. Instead of letting that thought remain in the minds of the student in some intuitive, nebulous form, ask the student, make the student get into the habit of putting that thought down on paper. And when you find students debugging code in labs, see if they have written a plan. Remind them that this will help them in debugging. Okay. Now, when you come to functions, the documentation changes slightly, the plan changes slightly. So here, what you should tell them is that before writing the body of the function, you should state very clearly what the function will return in relation to the inputs, the arguments of the function. So not just for the cases you think are going to get used, but also for other cases. Or at least you could say that, look, in these cases the function is going to return this. For these values, the function may do something funny, but I don't care about these values. So at least upfront, you will be stating that there is something wrong if the function is called with these values. Such statements are going to be very useful in debugging your code. Once you have given a description of program design, we continue on, and we continue with one more lecture on graphics, because this lecture is going to enable us to do interesting things for the rest of the semester. Okay, so this lecture is going to be about creation, manipulation and graphical input. Creation of graphical objects, manipulation of graphical objects and graphical input. So the first statement over here, circle C1 200, 225, 25 is going to create a circle. Its center is going to be at 200, 225 and radius is 25. The second statement is going to be creating a rectangle at center 200, 200. Its width and height will be respectively 50 and 70. Now, of course, I can use different names and I will get different rectangles. So if I want to create 10 rectangles, I can use 10 such statements. Okay. Now, introduce these statements as special statements for creating rectangles right now. But if you are familiar with C++, you will realize that these are actually constructors. So you don't have to tell that, because that's a technical term. The first few weeks, avoid using complicated technical terms. Constructor sounds really complicated. So just tell them that this statement is useful for creating rectangles. Now, if I want a rectangle to be rotated right, I can issue the command r1.right. I can write c1.move 1020 to move by 10 and 20 in the xy direction. Okay, so here now we are keeping track of the coordinate system. So there is a coordinate frame. It is located, its origin is located at the top left corner as usual. Okay, and here is an input statement. So if I write get click, it's like reading in values. Your program, instead of waiting for something to be typed, is going to be waiting for a click to happen. And Z will get 65536 times the x coordinate of the cursor at the time of the click plus the y coordinate. You may see that these are actually just simply saying that the most significant 16 bit should be the x coordinate and the least significant bit should be the y coordinate. And if the students wants to get back x and y, all he or she has to do is divide by 65536 and take the quotient as well as the remainder. Okay, if you do this, what have you accomplished? So first of all, it will be an implicit introduction to a constructor and member access syntax. Introduction performed reasonably painlessly because students understand these very, very precisely. And moreover, once students can create circles, squares and move them around, they will be able to do interesting animation. And to do interesting animation, they will have to use repeats, and so it will be practicing, they will get an occasion to practice repeats, and that is certainly core activity in computer science. And this has immense excitement value because elementary animation can be done already. This will provide examples and programming problems for weeks to come, and you will have pictorial analogues of everything that you study, and that will be very easy, that will make it very easy to understand many difficult concepts. So along with this lecture, you can have a projectile motion example. So here it goes. So you are going to, so for 2D graphics, instead of saying turtle sim, you are going to have this call initCanvas. So this will create a window of 500 by 500 pixels, and the title will be projectile motion. So you will get the starting point of where the projectile is going to be launched from by doing get click, and at that point you will create a circle. So SP is that starting point, SP is the circle that you created. So its center is going to be at the click point. That's what you get by dividing by 65536 and also taking the remainder, and the circle will have radius 5. And we are going to put the pen for that SP down. Okay. Now there is going to be a velocity, x and y velocities, and you are going to move that SP by the x and y velocities, Vx and Vy. But notice that Vy is changing, Vy is increasing, whereas Vx remains the same. So that is exactly like how projectiles move. The y velocity reduces because of gravity. Here it is increasing because of gravity, because remember that in our graphical system the y coordinate is growing downwards. So anyway, the y velocity is increasing and the x velocity is decreasing. So it will look like the way a projectile moves. Okay? And it will draw that projectile, it will make the movement for 100 steps, and at the end of it, it will stop. And then the picture will not go away until you click one more time. So that's the last click. The last click is there just so that the picture doesn't go away and you get to see the picture as long as you want to. Now this example on one hand serves as a demonstration of two-dimensional graphics, non-turtle based graphics. At the same time, it is hinting at one very important big idea in scientific computing. And what is that big idea? The big idea is about solving problems in the following manner. So at the beginning, I know what the state of the world is. I know how the world evolves at each step. And by knowing how the world evolves in a tiny fraction of time, in this case our tiny fraction of time is one step of that repeat loop, and that step might mean 1 microsecond for all we know. Okay, so in 1 microsecond we know how different things change. So the velocity changes. We don't know directly how the position changes, but we know how the velocity changes. So as a result, we can update the state of our world, and then we can show how our world is going to evolve. So this is a very simple system, just a single projectile, just a single ball thrown in the air. But you should point out that this is how many complex systems actually get simulated. And this is what might in fancy language be called Euler's method. Okay, so Euler iteration or first order Euler iteration, not 0th order. Okay? And indeed it's an important idea, although it's very simple. You can also do least squares fit. Okay, so we are given points and we want to fit a line to that, and the best fit line is some y equal to mx plus c. So we have to determine m and c, and we can determine m and c by following this formulae, and the exact values are calculated according to this. This is described in chapter 4, and it is an interesting example. It's an important example in these days of machine learning, but I will still say that this is not core material. This is tier 2 core. So decide whether you have time for it and whether your students are up to it. Okay? But the important point is that all this material is accessible even right now. We don't need if statements, just a simple repeat loop is adequate. Okay? So these are the formulae. So this is the code. Okay? So let me not dwell over the code, but the code is going to put circles where you click, and then it's going to calculate those PQRS as we decided earlier, and for that only a repeat loop is going to suffice. And then at the end of it, a line L, in the last line, a line is being constructed, so that line will get drawn. So the beauty of this is that you will actually be able to click points on the screen, and then a line will be fitted to what you click. Without graphics, the way this example would work is that you would have to input the values of x and y, and then the coefficients m and c of the line will get printed. Now that is not very easy to check even approximately whether those m and c are correct, whereas here you get a graphical demonstration. So it shows the power of graphics, and it also gives you an introduction to a very important area. After this, you should be talking about the if statement. Okay? So again, we should start all lectures by beginning, why are we teaching this? Okay? Here is a problem you cannot program without the new statement or using what you know already. Okay. After that, students are receptive to hearing you teach a new language feature. Okay, so what is the motivation for the if statement? Here is the motivation. You could say, suppose you want to calculate tax according to the following rules. If your annual income is less than 1,80,000, you pay no tax. If your annual income is between 1,80,001 and 5 lakhs, you pay 10% of your income above 1,80,000, and so on. Okay, so there are various rules. Now, as a taxpayer, which rule fits you requires us to know an if statement, or this is something that cannot be calculated using just repeats, and so therefore you need an if statement. This tax calculation is somehow a good example, but you may have your own favorite examples, and this example can be used to develop many programs. So for every tax bracket you could have a separate if statement, or you could have a one large if then else if statement for where each else if is for a different bracket. But there is some difference between the two, the conditions that you use in the two statements. In the second option, the conditions are going to be simpler because the else if clause is going to be executed only if the previous clauses have not been executed. Okay, so it is important to write a program in several ways, especially if it's not an easy statement. So you should show the student several ways of writing the same logic. Okay, and here flowcharts will definitely help students understand the difference between the two ways of writing the same logic. So this is where flowcharts I will recommend using, but this is for understanding a program, not really deriving a program. Okay, after that it's natural to talk about loops. So again you need to talk about motivation. So for the for loop, you should say, why isn't a repeat loop adequate? Well, you should say in a repeat loop you need to know upfront how many times the loop executes. Now here Soloway's rainfall problem that we have talked about earlier can come in handy. So the problem is, given a sequence of numbers terminated by 99999, which is a sentinel, find the average of all numbers except for 99999. So we don't know how many numbers are going to be there, and therefore The repeat cannot be used, so a while is needed. But with power, with great power comes great responsibility as well. So infinite looping is possible with a while loop. While loop gives you power, but it also gives you the responsibility of making sure that you are not going to loop an infinite number of times. So we need to argue termination. That is the responsibility that comes with the power of the while. Then termination arguments may be easy or difficult. A slightly difficult termination argument is for Euclid's GCD, and I will strongly recommend doing this. It is a classic algorithm, and it can be used as a theme throughout the course. So it can be used in recursion as well. Okay, so coming back to the rainfall problem, the rainfall problem loop really is read, test and process. So the test is in the middle. So which is typically implemented in two ways, by using code copying or by the break statement. So both of these ways should be talked about. Okay. So, and again, both of these ways are nicely explained using flowcharts. It is given in the book that we are talking about. And next comes the for loop. And the key point of the for loop is that you should use it whenever there is a natural control variable. If there is a control variable, tell your students, don't use the while loop. Make it your style, make it your programming style, that the for loop must be used if there is a control variable. And when you write a while loop, vaguely I know that there isn't a nice single control variable associated with this repetition that is being discussed. And students should be should have the skill or should have the ability to transform a program which uses a while loop to a for loop and vice versa. Okay. Many examples of loops are possible from scientific computing, physical simulation. Okay. These are really great examples. And at this point, you can tell them that the repeat statement is implemented using the for statement. And these loops are discussed in chapters 7 and 8 of the textbook that we have been talking about. The next topic is functions, and how do you motivate functions? Okay. So the most obvious use is that if you need the same code in several places, if you want the same set of operations to be performed in different parts of your program on different data, then functions give you a way of writing the code just once. Another but less obvious use to introductory students is that functions enable a program to be broken up into manageable pieces. I would say going with the first one as the main motivation and then introducing the second one later. How functions execute is a very important topic in my opinion, and I think you should explain this very, very clearly and very, very slowly. So for example, you should say that at the time of the call, an area in memory is allocated for storing the parameters and local variables that are needed while the call executes. So talk in very precise terms. That area is called activation frame. This is a compiler term, it's a technical term, but this is an important concept. So if it's an important concept, use a technical term. It signals to the student that something important is being discussed. And so the student is required to pay attention and give some care. Then the calling program suspends. Okay, copying happens, and when the return statement is executed, activation frame is deallocated. So I am not giving you all details over here. You know those details and they are discussed in the textbook as well. Okay? But why is this needed? So this is needed because it explains why local variables in the calling and called functions can have the same name. Because even if I say I, if I write it inside the function, then that I doesn't mean the variable in the main program. Okay? So the notions of scope and lifetime get very nicely understood if you talk very clearly about activation frames. The notion of copying and the notion of pass by reference also get understood very nicely. So this is discussed in chapter 9, and a byproduct of this is that if your explanation is good, students will automatically understand how recursive functions execute. I think along with functions, you should talk about references and pointers as well. References and pointers are useful in writing functions that return more than one result. Okay. So, the very natural way of doing that is to write reference arguments or pass arguments by pointers. Or if you want a function to modify the arguments, then you have to pass a reference or a pointer. Now, I feel that references are natural to be taught with functions, and I think most people will agree. Now, teaching of pointers can be deferred to arrays or structures, but when taught with arrays, there is additional complexity of index calculation. So, when you are introducing a concept, introduce it at the point at which you can talk about it with most simplicity, and therefore I suggest talking about pointers along with functions. And if you can also, you could also introduce them with structures, but then there is this whole business about referencing elements of the same type. So again, instead of that, I would say talk about pointers as a part of functions, although the two are not directly related. Okay, so you should say that they are not related, but you can use pointers if you want functions which modify their arguments or which return more than one result. When you teach functions and when you discuss pointers, then you only talk about the address of operator and the dereference operator. Okay? So these are two simple operators. You don't have to talk about the indexing operators, and these two simple operators can be discussed in isolation. Okay. Now, recursion is an important subject. Whether you should teach it in the first course or not has been discussed, but I should point out that it has many facets. So first of all, it's an algorithm design strategy. Okay. Euclid probably invented GCD algorithm by thinking recursively. But recursion also has a certain mechanics of execution. So more and more stack frames are created. So students must become familiar with both of these facets. And to make matters more exciting, there is structural recursion as well. So which of these things should you talk about? Well, introduction could be through Euclidean GCD, which I prefer, or you could use factorial because it is simpler. Okay, and Euclidean GCD, if you talk about, then its proof of correctness or proof of termination can be contrasted with the proof of the correctness of the iterative version or the plan you write in the iterative version. Okay. Mechanics of the execution actually show the activation frames that get created and encourage students to be able to show activation frames as exercise. Okay. Again, if you do this, you will be able to tell students that the function call mechanism is really the same. Recursive functions don't have any different mechanism. Okay? So that's the beauty of explaining that mechanism, because you explain it once and it will come in handy in explaining this supposedly more complex concept of recursion. And this is discussed in chapter 10. I want to say a little bit about structural recursion, because structural recursion is more known to students, because students know family trees. So students know that there can be a parent, but the parent will himself or herself have a parent, and so on. So there is sort of a natural notion of recursive relationship. So given such familiar structures, okay, familiar relationships, you can ask interesting problems. So for example, you could say persons are numbered 0 through n minus 1, and say for example array father with n elements contains values such that if father is -1, then the father of person I is not known. If father of some I is greater than 0, then father of I is actually the ID of the father of person I. So, for a person I, the array either tells you that look, we don't know who the father is, or the array tells you which number is the father of that person. So now you can ask something like, write a program that reads the number j and finds the oldest ancestor of j. Will a student be able to solve this problem if the array is given on the board? Definitely. Try it. Give it to students and ask them, can they solve it? And now can they do it using a C++ program or whatever programming language you use? For that, a natural thing will be to use recursion. Well, recursion will be even more natural for this program, where you say, find the number of descendants of j. So the natural idea will be, just don't look at all the direct descendants and then look at all the indirect descendants. So the indirect descendants will be most naturally found by using recursion. So many such relationship questions can be asked. It could be parents, it could be bosses. Okay. Now students will be able to solve them, while in the case of the array they will get practice with manipulating indices and also recursive thinking. Classical recursion, structural recursion is discussed in chapter 24, but you really don't need to do that. You can just do this example, and because this is such a familiar example, students will follow it, and it will also drive home the notion of recursion. You can also have pictorial recursion. So for example, I can think of a tree as a trunk plus 2 small trees, and this code puts that observation into practice. So it says that if I want to draw a tree with levels greater than 0, then it consists of a line obtained by moving the turtle forward, and that is the trunk. Then the turtle turns left and then draws a tree with one less level, or it draws the first smaller tree. Then the turtle comes back and now you turn again. This time you compensate for the 15 degrees you turned left, and you further turn 15 degrees to the right, and you draw a second smaller tree. So then you come back, and then you come back down your trunk, okay, because somehow you are sort of going to tell the user that look, this function is going to draw a tree. The turtle starts at the bottom of the trunk, it draws everything, and then it comes back again to the bottom of the trunk. Okay, so this code actually does draw a tree, but look at how simple it is. Look at the power of recursion. So it helps in understanding recursion, and it is also a good source of problems. Okay, well, as far as arrays are concerned, there are many uses of arrays. Unordered list or set. Roll numbers of students in a class need to be put in an unordered list or set. It can be an ordered list, so it can be used for queues, so it can be passengers waiting for taxis, for example. Or it could be a map. An array can serve as a map. So it maps the number 0 and -1 into array elements, and this is how it gets used in calculating histograms. So index calculation, deciding which actual variable gets used, requires the computer to decide, do an index calculation or to determine what a of I really means. So if we talk about pointers, then we can say that this requires an address calculation, and it can be done in constant time. And it also can be used to explain why a of I might go out of bounds if I is very large. Okay. So the pointer interpretation of a is quite important, especially because you want to pass a to functions. So these points need to be studied. Okay. So multidimensional arrays and representation of matrices should be discussed, but probably you don't have too much time, and probably it is better discussed as vectors of vectors So after you do the standard library. And null terminated character arrays should also be discussed, but again I would recommend not going overboard with both of these topics because they are better done using the standard libraries of C++. Structures are a starting point of object-oriented programming, and you should just about state that structures and classes are essentially the same in C++. Okay, there is only a small difference between the two things, and the motivation for structures is aggregation or composition, which is really an OOP idea, gathering together data or code associated with an entity. And from a programming philosophy point of view, what this is going to say is that you should represent every interesting entity using a structure. This is kind of the OOP principle. Member functions are natural and can be motivated. Constructors are motivated as a means to not forget to initialize. So therefore, I would like to put this as a core topic. Okay? So for example, I have a queue. If I put a constructor, then this next element will get initialized to 0. So the queue will sort of be well behaved and you won't have to remember to initialize it. Copy constructor, destructor, etc. are harder to motivate, and that's definitely not core material. It is tier 2 core. Operator overloading is not hard, but perhaps it is not worth the effort. So you could put it as tier 2 core as well. Encapsulation, inheritance and polymorphism are definitely harder to motivate, and therefore they are tier 2 core. Basics of memory management, heap memory, okay, using memory efficiently, storing names, each of which can be very short or very long, so you don't know how long the name is, so you can't declare an array very easily. Storing polygons of different number of sides. So you should teach in the core area, as a core topic, new and delete. Okay? And by the way, this is much safer than malloc. There is much more to memory management, but it should be discussed only if you have time, and it is really T2C, tier 2 core. Okay? So things about memory leaks and how to hide them behind constructors and destructors and things like that. The string and vector classes are great, and therefore I consider them to be core. So manipulating null terminated strings is really error prone. If you do not introduce string class, your students will continue to use null terminated strings, and that would be a great pity. So you should use string class. Vector class should also be considered core. Okay. If you don't teach again, students will learn linked lists, for example, and use those. And instead of linked lists, vectors are much easier, are very easy, and by and large, they can be used in most places that linked lists are used. And they are convenient even otherwise. They are convenient even more than arrays, because if you have a vector, it has a member function for size, and you don't have to pass the size when you pass a vector to a function. Then there is a library function for sorting, which is also really useful. So you can say that these classes use memory allocation, and we are not going to talk about how that happens. That is an advanced topic, and it could be taught as a tier 2 core topic. So it has been discussed in the book, but it is tier 2 core material. So the working environment, choices are, it could be a shell, some kind of a Unix shell or some shell, and an editor. If you choose an editor, then pick one that can do indentation. Okay. Encourage students to look at programs only after they are indented. Otherwise, you will not spot wrong nesting and things like that. We have modified the code blocks IDE, so you can use it. So it has been modified to allow single file programs. So I am going to conclude in a few minutes, but I want to point out that graphics and repeat turn out to be really useful in this entire exercise. So they enable discussing interesting problems from day one. It is useful throughout the course for generating interesting homeworks and classroom problems. Repeat is useful until standard looping statements are taught, which might happen as late as a month into the course. So instead of doing dull examples with repeat, you can have very interesting examples. Having good programming examples is very useful to make students remember concepts, and that is accomplished by using graphics and repeat. So graphics is also useful for explaining concepts. You can use it to draw trees, and trees are sort of recursion in action. So you can see that, oh, I'm going to draw the left side first, and indeed the left side appears first in your recursive code. So the correspondence between the drawing and the program is very interesting to students. Repeat is halfway to a standard looping construct, so it breaks down the difficulty of understanding looping constructs. Graphics and repeat are very easy to learn, and so in my opinion they are ideal scaffolding. Okay. Just like training wheels on children's bikes. My experience has been that even the weakest students understand turtle movement and repeat, and this understanding gives them confidence to write programs. And so please, please, please use this. Your students will love you for it. So to conclude, what we did was we presented the basic ideas behind our pedagogy. Okay. And we only talked about the core syllabus. We'll talk about the other part, the T2C part, a little bit later. Pedagogy for the advanced topics and design of examinations is what we will talk later on. These are the references, and so that brings us to the end of this sequence of lectures. Thank you.